Now let's proceed. In chapter 10, what we're going to discuss is to use transfer function to solve a problem related to passive electrical network. Okay. Now, the network we're going to solve is actually RLC circuit. I believe you all maybe heard about these RLC circuits before, but just do some let's do some recap on RLC circuits. The RLC circuits actually consist of three components, basic components, which is resistor. We know about resistor, right? Basically, it's a passive two-terminal electrical components that we can actually use to reduce current flow. And when current flow through it, the part of the electrical current will lose as heat. And then we also can use it to adjust the signal level, whether it's low or high. Oh, no, sorry, from high to low. And also, we can actually use it to divide voltage. If we connect them in series, say we put four resistors in series circles, then we can actually divide the voltage for in each of the resistor. Right, this is about resistor. And then when we discuss about resistor, we will actually relate it with Ohm's law, where it actually stated V equal to IR. The current flow through the resistor when we apply voltage across it is equal to the voltage divided by R. Okay, the ratio. This is about resistor. Then we go to capacitor. Capacitor is a device that we can actually store energy. Now on your right hand side here, okay, this is a simple setup for capacitors where we actually sandwich a dielectric layer between two conductor plates. Now, if we apply voltage across this conductor plate, what's going to happen is we're going to build up charge in the dielectric layer. So in this case, here is positive charge. Then this part, the dielectric is going to have a negative charge. And if we have a negative charge over here on the conductors, then this sides of dielectric, we're going to have a positive charge. Okay. Now, what's going to happen is when you have a positive charge over here and negative charge on this side, is going to build internal electric field that cancel off the external electric field built by the conductor. In short, the capacitors can actually store the electrical energy in electric field form. Now, we can actually use capacitor for many applications. One of it is to store energy, like battery. I believe some of you might work your FYP in futures under Dr. Azimin. He actually have some work on this, actually building some dielectric layer to store the energy. Then you can use it as a digital memory, where if the capacitor carry charge, then it become 1. If there's no charge, it becomes 0. Then we can actually build a binary code 1010. Right. Another application is on pulse power. The one that we're very familiar is laser. Now we can actually use capacitors to store charge and then discharge it at a very short period of time. And it's going to actually produce high intensity of light. Right. So this is general use of capacitors. Now the last component is inductor. We can actually make inductors easily. What we can actually use is we have this insulated wire. We can wound along a coil, a conductive coil, and when we actually pass AC into it, the electric field is going to cut through this coil, and then is going to induce current, right? And this current is actually oppose the flow of the electrical current in the wire, right? And it's going to also generate magnetic field. In short, inductors can actually store energy in magnetic field, right? And the unit that we use is Henry H here. H. Henry. We could actually use inductor in many applications again. It used normally as a choke to block or limit AC while allowing a small amount or control amount of DC to pass through it. The example I can give that we normally use is actually the fluorescent lamp, the white lamp that we use. Now, you open up the casing, you can see a ballast inside. In the ballast, actually, we have this inductor inside. It helps to start up the fluorescent lamp. At the same time, it regulates the current flow between the two terminals of your fluorescent lamp. Therefore, we have a consistent light intensity come off from the fluorescent lamp. Right. This is something about inductor. Any questions you want to ask before we move on to LC? Any questions you can type or you want to ask now? No problem. You can open the mic. Okay. Oh, okay. Atika. Okay. No problem. Right. How many of you is right? Let's now look at the LCR circuit. Now, before we move to LCR circuit, we discuss about LC circuit. The LC circuit composed of two components. One is inductor and one is capacitors. If there is a way, we can actually connect external power supply, and then we apply current, apply voltage across this circuit, and then we remove the external power supply. Now, what is going to happen is the current is going to flow in this circuit, right? When it flow in the inductor, it is going to actually build magnetic field inside the inductor, right? And this inductor, now this magnetic field is going to actually, how do I say, release the energy again and become current flow into the circuit, and it's going to actually store. Is going to actually build charge at the capacitors in the form of electric field. And then the electric field inside, or the energy inside this capacitor, is going to discharge again, and it's going to cause current flow into the circuit, flow into the inductors again, and start to build magnetic field. Now, this process can actually move on. The charge can actually flow back and forth between the capacitors and the inductors. And then theoretically, if there's no loss of energy, this process can go on for a long time. Now, this is the characteristic for LC circuits. If we actually install one more component inside, resistor. Now, what's going to happen is when this charge flowing in the circuit, the resistors, when the current flow through the resistor, is going to actually lost energy as heat slowly, okay? And then after a certain while, you can see the current die off. Now, we call this effect as a damping effect, okay? We call this effect as damping effect. Now, RLC circuit, we actually use it in our daily life. I believe we all use radio before, okay? Radio before. When we adjust the knob, we actually try to tune the RLC circuits here to a certain frequency. Okay, so this is one of the common example that I can give, right? RLC circuits. Now, today's topic we're going to actually discuss is actually to solve problem related to these RLC circuits. Okay, questions? Anyone? To find just a brief intro on RLC circuits. Let's move on to these RLC circuits. All right, in RLC circuits, we're trying to solve these so-called electrical network. There are two types generally. Sorry. One is called single loop network. What we have is just one loop here. That will be very simple, right? The one I would like you all to pay attention is this multiple loop electrical network. It consists more than one loop. So this is what you see, 1, 2, 3. Okay. Let's look at the first one here, how we can actually use the Laplace transform to solve this problem, right? There are 4 steps actually. The first one is to decide input and output. The second step is to convert each component from a time domain to frequency domain. And the third step is to get the relationship between voltage and current using Ohm's law. And the third one is to get the transfer functions between the output and input. All right, I'm going through all these steps one by one to you. Now, if you look at this one, step 1 is to determine the input and output. Now, in your test or in your exam later on, I think there's no exam, there will be only test. Okay, you have to read carefully on the questions. Okay, it is going to actually state very clearly. Input normally no problem because only there's only one input normally in the questions, which is this one. Now the output, it can be the voltage of capacitor, voltage of resistor, voltage of inductor, or even the current flow in the circuit. So you all need to read carefully the questions in the test. Right. This is about step 1. So in this step 1, so you have input is supply voltage, which is this one, and the output is the capacitor voltage, which is this one. Right. Now let's move on. Now step 2, we need to convert the elements from the time domain into frequency domain. Now this is the conversion table. Okay. For capacitors, the initially is C, capacitor time domain is C. So when we want to change to frequency domain is 1 over CS, right? For resistor is R, in frequency domain is still R, no change.
No, kata
Okay, can you all switch off the mic? And for inductor, the form in a frequency domain is LS. In time domain, it's just L. In frequency domain, is LS, right? So you all need to actually know about the conversions. In test, I'm not given to you all this table, but I think it's relatively easy. Okay. Now let's see how we change. Now in time domain, we have LRC. Okay. When we convert it into frequency domain, L will become LS. R will remain the same. C, capacitor, capacitance will become 1 over CS. 1 over CS. Right? Is that okay? LS, R will remain the same. C will become 1 over CS. That's it. Right. So what is done, the next thing is to get the relationship between the voltage and current using Ohm's law. Using Ohm's law, that will be very easy. So we have the input, which is V, S, sorry. Now, for voltage, the input voltage in time domain is Vt, but in frequency domain is Vs, right? The current flow in time domain is It, but in frequency domain we change to big Is, right? And in step 3, we can actually get the relationship between voltage and current. How we get it? Voltage referring to this input voltage, and the current flow through in this loop, right? So we'll just add up the impedance in this loop. So I multiply Ls plus I multiply R plus I multiply 1 over CS. So this is the equation view. V equal to bracket Ls plus R plus 1 over CS multiply Is. This is our first equation. Is that okay? Can you follow? Now if okay, then we move on to the next one. Now remember, just now we say the output is VC. Okay, we want to know the output is actually the output. So VC is equal to 1 over CS multiply I. Okay, this part, the impedance for the capacitors. VC equal to 1 over CS multiplied I. Right. So we have this, our second equation. Just now we have first equation and we have a second equation. Now what I'm going to do is actually substitute the this equation 1 into 2. All right. And you're supposed to get this equation. You're supposed to get this equation. You substitute your equation 1 into 2, you're supposed to get this equation. Right. And when it's done, if you still remember the transfer function, our transfer function is actually equal to the output divided by input, right? Our one output is VC, and our input is V. Right. So what you need to do is to rearrange this equation, right? So we have VC here, we have V over here. So we move V into this side, and we move all these components, to the other side. And this will be our answer. Yeah, halfway answer. Actually, still we need to work on. Is 1 over CLS squared plus CLS plus 1. Okay, we'll stop here, but actually we still need to work it until time domain. We need to do partial fractional expansion, and after that we do inverse Laplace to get the solution, the answer in the time domain. But for this slide, we'll just stop here. Is there any questions? No, you need to ask before you move to a multiple loop, because when you go to multiple loop, it is slightly complicated. Any questions? Can you actually, if you have, then you can either type in the chat box, or you can actually switch on your mic. Can follow? Sorry, take coffee a bit. Is there any questions? No. Okay.
No
right.
question.
No question, right? Can follow. Right, good. Then we will start to look at the multiple loop. Right, we have two loops here. Same approach we're going to use just now. Just a slight difference is, if we look carefully on this graph here, we have one component, okay, is actually sharing by two loops. Okay, so therefore later on we need to actually minus away the impedance contributed by I2 multiply LS. Sorry, I2 multiply LS. Right. So how it works? Same thing. First, we need to decide input and output. Okay. So the input is this one, VT, and the output. Okay. If you look carefully, the output here, what the question one is current I2. What we want is I2. Okay. Right. We just know it. Then we move to step 2. We're going to convert it from time domain to frequency domain. Right. Resistor remain the same. R2 here is R2. L in time domain is LS. C is 1 over CS. Okay, and we change here is VS. We change here is IS, I1S, I2S. All right. Questions? No? Yes? Can follow? If no questions, we'll move on. You have to either, if you have questions, please ask here. Right. So next thing we need to do is to build the equations. Right. So generally, if we have two loops, we can actually build two equations from each loop. Right. So how you do is sum impedance around the loops, and then we minus impedance share with other loops. So what we do for loop 1, okay, for loop 1's current flow in this direction, so therefore we have I1 R1 plus LS I1. Okay, now we have to minus impedance share with other loops, means we have to minus away this component shared by other loops, so which is negative I2 multiply LS. Get it? and is equal to our input. Is that okay? We have loops here, so therefore, when you flow, the impedance generated by this component will be R1 I1 plus LS I1, okay? And because this one is shared by this loop, so we have to minus away the impedance, which is minus LS multiplied I2 and equal to V. Right. Now let's look at for loop 2 again, I2. So I2 we flow in these loops, and there are 3 components. So we have R2 plus I1 over CS plus LS bracket multiply I2 minus LS multiply I1 equal to 0. Is that okay? Your I2 flowing in this loop, so with I2 multiply R2, I2 multiply I1 over CS, I2 multiply LS, and then minus I1 multiply LS equal to 0. All right, so we have a second equation. Now when we have first and second equations, we can arrange them in the matrix format. Right. So we have here, we rearrange it, we can actually get this in a matrix format. Right. So if you multiply back again, this one multiply this negative IS multiply I2S equal to VS. You're going to get back first equation, and for the bottom, you're going to get the second equation back. Right. So D is in matrix format. Can you still remember how to actually build this matrix format? Hope you all still remember. I believe Dr. Siva taught you all before on this. Right, when it's done, well, if you are given the value for your R1, R2, L, and C, you actually start to substitute this value into your matrix, so as it simplified the format. It make you easier later on when you want to rearrange your solution. Okay, so if you substitute this value inside here, okay, you are going to get this form, right? And the next thing we need to do is use the Cramer rules to find the solution for I1 and I2. Hope you all still remember the Cramer rule. This is how you actually look like for 2x2 matrix. Okay, and if you still remember just now the questions, they want to find the question want us to find I2 divided by B. So you'll just look at this one. Okay, you'll just look at this, right? And so you're going to solve this I2. So 1 plus S multiplied 0, we get 0, and minus XV, so we get V multiply S, right? And divide by the denominator. So how we get this denominator is this one multiply this component minus S squared. So you're going to get this, right? And then we rearrange the terms over here, okay? And what we're going to get is this answer. S squared V divided by negative x3 plus S plus 1 bracket S squared plus S plus 1. Now, this is our I2, right? And then later on will be very easy. The questions want us to find I2 over V. So what you need to do is just move the V from this side to here. And then the remaining term over this side will be our answer. Right, this will be your answer. Okay. Again, I stop here, but in fact, it's supposed not to stop here. We need to do a partial fractional expansion, and then later on do an inverse Laplace transform to get the answer in time domain. Right? Any questions here? Oh yes. Before we move to multiple loops. Questions? No? We need to minus it because different direction. Yes. Loop. For Hazim, it is actually not because it's different direction, it's because of different loops. Right, now if you look at the circle again, right? This is loop number 1, and this is loop number 2, okay? And from loop 1, we can generate one equation. From loop 2, we can generate another equation, right? So let's look at here, loop 1. So the current I1 is flowing from here, right? It's actually flowing from here. So it's going to pass through R1 and LS. So when pass through R1 and LS is going to generate one impedance from R1. We can get one impedance from R1. We can get the second impedance from LS, right? So this is what we get, R1 LS. Okay. But then if we look carefully on this component, it's actually shared by the second loop. So therefore, we need to minus away the impedance actually sharing by this component with other loops. So you see is negative LS multiplied I2, right, is equal to V, right? So if you look at loop 2, we have I2 flowing into this circuit, right? So we're going to generate impedance from R2 from the capacitor 1 over CS, which is this one, and also from the inductor LS, right? So we have these three components here. But then again, this component is sharing by with loop 1. So we need to minus this impedance away, right? So this component is ILS multiplied I1, yeah, not I2, I1. Okay, and then we get the second equation. Then we will move on. Any other questions before we move to a multiple loop? Is going to actually more and more tough. About S2, the S2.
Doctor, from the matrix formula.
Matrix formula. Just on, yeah. Here. Is that here? How we get S2? Right.
Yes.
This one, right?
Yes.
Then you know how to get this I1 and I2, right? So how we actually get the S2? Oh, they actually have arrangements over here. R2 is 1, C is also 1, so you get 1 over S plus S. If you rearrange it again, this term over here, you are going to actually get X squared plus S plus 1 over S. You multiply it with now over here you have 1 over S, right? So if you multiply S on top and multiply S at the bottom, the denominator, you are going to actually get this term, S squared plus S plus 1 over S. Now let's look at the transfer function for when we have 3 loops. Same thing again, we are going to use the approach that we discussed just now to generate equations. Now if we have 3 loops here, means we have 3 equations. Same thing we will need to do. Decide the input and output is given in the questions. Input always have 1. Output, what the question 1 is the capacitor's voltage, which is VC, which actually referring to because there's only one capacitor in the circuit, right? The next thing we need to do is to convert the the circuit into time domain to frequency domain. This already convert for us, right? What you see here is already convert from time domain to frequency domain. This is already in the frequency domain, right? So no problem. Then we move to step 3 to get the relationship between the voltage and current. Okay. So since you have 3 loops, we're supposed to get 3 equations. Now let's look at loop 1. Loop 1. So I1 is going to flow through these 3 components. So this is resistor 1, 1. So we have 2 plus 2s. Bracket multiply I1. This is I1. Okay. This one no problem, right? Then remember we have to minus impedance share with other loops. Let's look at loop 2, which is this one. Right. The component actually sharing with loop 2 is this one and this one. Right. So what we need to do is 1 plus 2s with bracket multiply I2 and put a negative sign. Right. 1 plus 2s bracket multiply I2 minus, because we have to minus away the share impedance. Right. And we look at the loop 3. The one sharing with loop 1 is this component. So therefore, it's just simply minus 1 multiply I3. Minus 1 multiply I3. And is equal to the input V. So just repeat, right? Loop 1, the impedance generated by I1 is this one plus this one plus this one. So we have 2, 1 plus 1 is 2 plus 2s. Okay, bracket I1. And then we have the share components with loop 2. So this is 1 plus 2s, bracket multiply I2. And then we have a share components with loop 3 over here. So therefore we have negative 1 multiply I3. And it's equal to the input. Right, if not, then we move on to the next equations, loop 2, which is this one. Right, loop 2 is you have 1, 2, 3, 4 components, and current is I2. Right, so therefore the impedance generated by the I2 will be 4s plus 3s plus 2s, which is 9s. Okay, plus 1. So you bracket I2. So this impedance generated by I2, right? And it's actually share these two components with I1. So this component is 1 plus 2s, 1 plus 2s bracket multiply I1, and you put a negative sign. Okay, 1 plus 2s because it's sharing with these loops, these two components, right? Brackets I1 and minus. And then we look at the component share with loop 3, which is this one, right? So it will be 4s multiply I3, you put a minus sign, equal to 0. Now let's look at loop 3. So in loop 3, we have 3 components here, and the current flow is I3. So what we have here will be 1s plus 4s, 1 over s plus 4s plus 1. So these are components we have, I3, right? The one shared with loop 1 is this component, right? So is 1 multiply I1, negative 1 multiply I1, right? And I2, the component shared with loop 2 is this one, right? So is 4s multiply I2, a negative sign. And the whole equations will be this one, right? So from here we have 3 equations. 1, 2, 3. Again, we arrange it in a matrix form, 3 by 3. And again, we have to actually solve this using Cramer rules. Now, to solve 2 by 2 will be relatively easy using Cramer rules, but to solve 3 by 3 and above, we're going to take some time, right? So I want you all to actually do it, trying to do it, solve it 3 by 3. Okay, another way is actually using MATLAB, which unfortunately we did not discuss in this. I don't think we are able to cover MATLAB, and also to show you how to solve it 3 by 3 in this course. But I just tell that we can actually using MATLAB to solve, and this will be the answer. This will be the answer. Now I want you all to try to solve it manually using Kangaroo, and this will be the answer for your solution, for your question. Sorry. In the test, if there's any questions come out from this part, it will actually stop at maximum is 3 equation, 3 loops. That's it. Either 1 loop, I don't think it'll be 1 loop or 3 easy. Either 2 loops or 3 loops. Okay. Yeah, this will be the answer. Any questions?